If you take two molecules of a simple ester, like ethyl acetate, and add a strong base, something remarkable happens. They don't just sit there. Instead, they link up, shedding a small piece of themselves to form a much more complex and useful structure, a beta-keto ester. This is the Claisen condensation, and it's one of the most elegant ways in organic chemistry to build carbon-carbon bonds. To understand how it works, let's go beyond the flat lines of a textbook and visualize the electronic push and pull happening at the molecular level. Let's look at our starting ester. Notice the oxygen double bonded to a carbon. This is the carbonyl group, and it's the star of the show. It's highly polar, meaning it pulls electron density away from the neighboring carbon, what we call the alpha carbon. Because of this, the hydrogens attached to that alpha carbon are unusually loose or acidic. Now, watch what happens when we introduce a base, specifically an alkoxide. The base swoops in and snatches one of those alpha protons. As the proton leaves, it leaves its electrons behind, creating a negatively charged species called an enolate. Think of this enolate as a primed spring, loaded with nucleophilic energy and looking for a place to attack. And here's the key insight. In a flask full of ester, that enolate doesn't have to look far. It finds a second, neutral ester molecule. Let's visualize the collision. The enolate attacks the carbonyl carbon of the second ester. As you can see here, the carbon-oxygen double bond breaks, pushing electrons up onto the oxygen to form a tetrahedral intermediate. This is a crowded, high-energy state. It's unstable, and the molecule wants to collapse back down to a more stable form. But it has a choice. It can kick off the enolate it just joined with, which would take us right back to the start, or, and this is the magic of the Claisen, it can kick off the alkoxy group. Since the alkoxy group is a decent leaving group, the carbonyl double bond reforms, and we are left with a brand new carbon-carbon bond holding two ester fragments together. But wait, we aren't quite done. If you look at the product, you'll see it has a central carbon trapped between two carbonyls. This position is incredibly acidic, much more so than our original starting material. The base we used earlier will immediately deprotonate this spot, forming a highly stable, resonance-stabilized salt. This final step is actually the driving force that pulls the whole equilibrium forward. To get our final neutral product, we just add a splash of acid at the very end to put that proton back. So, why does this matter? The Claisen condensation isn't just a clever trick, it's a fundamental building block. By joining two simple esters, we've created a molecule with two distinct reactive handles, perfectly spaced apart. It's a testament to the idea that in chemistry, the most complex structures are often just the result of a simple dance between a site that has too many electrons and a site that wants them. Once you see the push and pull of the electrons, the mechanism isn't something to memorize, it's something you can feel.